Good morning to one and all. Today in this lecture video, I am going to explain about AC voltage controller. So let me share the PPT first. So these are the outline of the presentation. So out of all these topics, now I am going to elaborate about single phase AC voltage controller. So as you know, the AC voltage controller is a static power electronics converter which will convert the fixed AC input power to a variable AC output power with variation in voltage only, which means the input frequency and the output frequency are constant. And here you can see the power electronics converter which will be having maybe one thyristor, two thyristor, one thyristor and one diode, that will convert a fixed AC to a variable AC with variation in voltage with constant frequency. So now in India, the supply frequency is standard frequency is 50 Hz. So to complete one cycle, 1 by 50 means 20 milliseconds. So in 20 milliseconds, there will be one complete cycle, right, at the input side. Similarly, at the output side also, if I see from 0 to 2 pi, you can see one cycle. So in one cycle, we need to complete one positive half cycle and one negative half cycle. And it is completing, it will complete in 20, it has to complete in 20 milliseconds. So 1 by 20, it will give a 50 Hz. So there is no change over the frequency, but the voltage can be varied by varying the area under either positive half cycle or negative half cycle or both. So depending upon the application, we can go for this AC voltage controller, and these are the applications we can see here. Some of the applications, one speed control of a polyphase induction motor, and speed control of synchronous motor also, and domestic and industrial heating, light control, on-load tap changing, transformer, static reactive power compensator. So these are the few applications where you can find the AC voltage controller, right? So if I want to control only the positive half cycle, if I want to control only the positive half cycle or only the negative half cycle, and that is called AC half-wave AC voltage controller. Half-wave AC voltage controller. If I want to control both positive and negative half cycle, then that is called full wave AC voltage controller. Right? We'll see one by one. So first we'll go for single phase half wave AC voltage controller, which is also called as unidirectional AC voltage controller. And this is the circuit configuration. So here you can see thyristor and diode which are connected in anti-parallel to each other. So which means one half cycle will be controlled by this thyristor T, and other half cycle will be, we cannot control the other half cycle because we are using an uncontrolled device here. If I use a control device here, then we can control positive half cycle with T1, negative half cycle with T2. So since it is a half-wave AC voltage controller, we are using only one control device, right? So first we'll go for resistive load. So here you can see the load, which is a resistor, and this load is connected to source through the power electronics converter, which is having one thyristor and one diode, which are connected in anti-parallel. So the input to the thyristor, input to the power converter is a AC. So you can see VAC or V input, which is Vm sine omega t, and you can see the AC waveform like this. And it is completing one cycle in 2 pi radians or 360 degree. Within 360 degrees, it will be completing one cycle. So first we'll go for positive half cycle. So during positive half cycle, let us say this is at higher potential and this terminal is at lower potential. And if that is the case, you can see the thyristor anode here, which is connected to positive terminal or higher potential. And cathode of thyristor T is connected to negative or lower potential to load. So which means thyristor will be in forward bias condition. And we can make it on with the help of gate terminal. So at omega t equal to alpha, if I apply gate pulse, then from omega t equal to alpha onward, T will conduct and it is replaced by short circuit. It will be replacing with a short circuit, and voltage across the thyristor will be 1 to 2 volts practically, and ideally it has to be 0. And from omega t equal to alpha onwards, the load will be subjected to source voltage, which means the load voltage will be following the source voltage, which is a dotted line that you can see here. And since diode, let us see the diode, which is connected in anti-parallel. So cathode of diode is connected to higher potential, anode may be connected to lower potential through the load. So diode will be in reverse bias condition, it will goes to off state automatically. So there is no role of diode during positive half cycle, it will be in off state. It will be in off state, and the current will flow like this from higher potential through thyristor, anode, cathode, load, and back to the source, which is a lower potential. And see, the direction is from top to bottom, right? So, and since from omega t equal to alpha to pi, even though diode it is a reverse bias condition, but the anode of diode is connected to cathode of thyristor, cathode of diode is connected to anode of thyristor. So which means from omega t equal to alpha onwards, the voltage across the thyristor will be same as the voltage across the diode because they are connected in anti-parallel. And you can see from 1 to 2 volts across the diode, and since they are connected anti-parallel, you will get negative voltage across it, right? So let us focus on the negative half cycle. So negative half cycle will start from pi to 2 pi. So this is negative half cycle. So previously I said that it is at higher potential, it is at lower potential during positive half cycle. So now during negative half cycle, the polarity will reverse. So now this polarity will be at lower terminal or minus negative terminal, and this polarity terminal will be at higher potential, right? So now the polarity is getting reversed. Now this is the behavior of AC voltage controller. Anode of T will be connected to lower potential, cathode will be connected to higher potential. So thyristor T will be in reverse bias condition and it will be in off state. Whereas let us focus on diode. Diode cathode is connected to lower potential, anode is connected to higher potential through load. So since it is an uncontrolled device, at the moment it is in forward bias condition, it will conduct and it will carry the current. This conduction of the diode will be replaced by short circuit. So, and the current will flow from higher potential to lower potential. Higher potential is positive, load, diode anode, diode cathode, and to the lower potential like this. So the direction of current, it is from bottom to top. The reversal of current is taking place here. So from pi to 2 pi, the diode will be in conduction state, and the load will be subjected to source through the diode. So while getting complete negative half cycle, there is no control over the negative half cycle because we are using a diode here, which is an uncontrolled device. And this diode and thyristor, again, they are connected in anti-parallel. So voltage across the diode will be the voltage across the thyristor. So that is why you are getting 1 to 2 volts across the thyristor also, but with negative because they are connected in anti-parallel. So this is the waveforms. Then from the waveform, we will try to extract the voltage across the load. So to extract the voltage across the load, we'll focus on the output voltage waveform. So you can see this is the output voltage waveform. So in one cycle, we'll be having positive half cycle as well as negative half cycle. So positive half cycle will be from alpha to pi, and from pi to 2 pi, there is a negative half cycle. So we are splitting the pi interval, 2 pi interval into two halves. So because of non-symmetrical waveform, because during positive half cycle we are getting the waveform from alpha to pi, whereas from during negative half cycle we are getting the waveform from pi to 2 pi. So that is why we are splitting this integral into alpha to pi Vm sin omega t and pi to 2 pi Vm sin omega t. So integration of sin omega t will be minus cos omega t, and you can take Vm common, it is Vm by 2 pi. So minus cos omega t, the limits are alpha to pi, and the minus cos omega t again, so limits are pi to 2 pi. So if I substitute here the upper limit as lower limit, so Vm by 2 pi minus cos upper limit, which is pi, minus into minus plus cos lower limit alpha, minus cos upper limit is 2 pi, minus into minus plus cos lower limit is pi. And if I solve this one, I will get Vm by 2 pi cos alpha minus 1. So for this configuration, blindly I can say the area under negative half cycle will be more, which is from pi to 2 pi, whereas the area under positive half cycle will be from alpha to pi. So this area will be less when compared to this negative area. So if I substitute any value of alpha, which is from alpha equals 0 to 180 degrees, you will get negative voltage across the load, because area under this negative half cycle will be more when compared to the area under positive half cycle. So this is the output voltage. Similar, I can calculate the output current, which is output voltage divided by the resistor. So Vm by 2 pi r cos alpha minus 1, where Vm equal √2 times the supply voltage. So similarly, we can go for the RMS output voltage derivation. So which is again alpha to 2 pi Vm square sin square omega t under root. So root means mean means 1 by 2 pi, square means Vm square sin square omega t d omega t. Again, sin square, due to non-symmetrical waveform, we'll consider separately alpha to pi during positive half cycle and pi to 2 pi during negative half cycle. And let us substitute the upper limit and lower limit. So it is sin square omega t can be written as V 1 minus cos 2 omega t by 2. And we assume that the waveform is a continuous conduction operation. So from alpha to 2 pi, there is a continuous current. So directly also I can take, that is why I took from alpha to 2 pi directly. And even if you split, you will get the same response, but I have taken directly here. So do the integration and substitute the upper limit or lower limit, we'll get the RMS output voltage as Vm by 2 root pi under root 2 pi minus alpha plus 1 by 2 sin 2 alpha, right? And I can calculate the current dividing the voltage by R. So Vm by 2 pi 2R under root pi under root 2 pi minus alpha plus 1 by 2 sin 2 alpha. This is the RMS output current. So if you know the operating principle, you can easily draw the waveform, and from the waveform you can extract the derivation part, right? So this is about a single phase half wave AC voltage controller with resistive load. And now we'll go for RL load. Just replace the load with R and L. So you can see the inductor and resistor, they are connected in series. And here we are going to measure the load voltage, right? So as I have explained just now that during positive half cycle, T1 thyristor will be in forward bias condition, whereas diode will be in reverse bias condition. Same you can see here. So that is why diode will be in off state, whereas thyristor will be in conduction state whenever you apply the triggering pulse. So at omega t equal to alpha, I have given triggering pulse to thyristor T, and which will make the thyristor to turn it on, right? And during negative half cycle, as we have discussed already, diode will be in forward bias condition and it will goes to on state directly from pi to 2 pi because it is a uncontrolled device. And thyristor will be in reverse bias condition, so it will goes to off state, right? So with this operating principle, let us focus on the waveform. So here you can see the waveform. The only difference between resistive load and the inductive load is that in case of resistive load, the current and the voltage, output current and the output voltage, they are in phase. But in case of resistive inductive load, there is a lag in the current, and the lag is given by tan inverse omega L by R. So depending upon the value of omega, which is 2 pi f, L and R, there is a lag in the current from the output voltage, right? So as I said, at omega t equal to alpha, firing pulse is given to thyristor T. So from this particular point onward, the output voltage will be uh, following the input voltage, which is a dotted line, because this load will be connected to source through this thyristor T, and due to the load, inductive load, the current will lag the voltage by some angle, thereafter it will charge and discharge, right? And thyristor T, it is in conduction state from alpha to beta. So thyristor T will be in conduction state and the voltage across thyristor will be 1 to 2 volts, right? And since T and D, they are connected in anti-parallel, voltage across the diode will be same as the voltage across the thyristor, but with reverse. So I can see 1 to 2 volts, which is -1. Right? So this is during positive half cycle. Similarly, during negative half cycle, so thyristor will be in reverse bias condition, whereas diode will be in forward bias condition. Since it is an uncontrolled device, so during negative half cycle, this will be at lower potential and this will be a higher potential. The current will take place from higher potential to lower potential through load and diode like this. And there is a reversal voltage across the load. That is why you can see from alpha to pi to 2 pi, the output voltage will be same as the input voltage. And there is a lag in the current, and you can see the current wave shape like this. So after having this waveform, we'll see the derivation of average output voltage and RMS output voltage. So due to non-symmetrical waveform, I can split from alpha to pi and pi to 2 pi. But I have taken the integration from alpha to pi plus alpha. So due to presence of inductor in the load, large value of inductor in the load, I am getting continuous current. That is why you can see the output voltage waveform from alpha to pi plus beta, right? So alpha to pi plus beta, Vm sine omega t into d omega t. You do the integration of sine omega t will be minus cos omega t, and the limits are alpha to pi plus beta. And if I substitute the upper limit or lower limit, this will be the expression of average output voltage Vm by 2 pi cos alpha plus cos beta, where beta is the extinction angle, and the definition of extinction angle already given to you. It is the angle measured from the reference point to the point at which the current extinguishes to zero. So here at this particular point, the current will be extinguishes to zero. That is why it is called beta. So similar, you can find out the current which is average output voltage by the impedance, which is Z, right? Similarly, I can go for the derivation of RMS output voltage. So it is 1 by 2 pi root over 1 by 2 pi integration from alpha to pi plus beta Vm square sin square omega t d omega t. So sin square omega t is 1 minus cos 2 omega t by 2, and I can take the Vm square out of the root, which is Vm by under root 2 pi, and if I substitute instead of sin square omega t, it is 1 minus cos 2 omega t by 2. I can take 2 as common. Root 2 into root 2, it will be 2. So Vm by 2 root pi under root, the leftover quantity is 1 into d omega t, and here it will be minus cos 2 omega t d omega t. So do the integration, and after substituting the upper limit or lower limit, I will get the RMS output voltage as Vm by 2 root pi under root pi plus beta minus alpha minus 1 by 2 sine 2 alpha minus sine 2 beta, sine 2 beta minus sine 2 alpha, right? So this is the RMS output voltage. You can also calculate the RMS output current, which is Vm by Z, V naught RMS by Z, and this is the expression for the RMS output current, right? So now we'll go for one simple problem here. So here you can see single phase 230 volts, 50 Hz half-wave AC voltage controller feeds power to a resistive load of 20 ohms, right? So this is with resistive load, and the thyristor is fired at an angle of 45 degrees. So alpha he has given 45 degrees. Calculate the following factors: average output voltage and current, RMS output voltage and current, and input power factor of the converter. So which is asked in the external exam in May 2019. So let us see the given parameter. Vm will be, as I said, it is V supply into root 2. So V supply is 230 into root 2. Firing angle alpha has given, resistor also has given. Only we need to calculate the average output voltage and current, RMS output voltage and current input power factor. So this is the expression for average output voltage, which is Vm by 2 pi cos alpha minus 1. So we know Vm, which is 230 into root 2, right? And which will give it as 230 into root 2. It has 325.25. And cos alpha, it is 45 degrees. So if I substitute here, you will get the average output voltage as minus 1.16, right? Similarly, I can calculate the current, which is V naught RMS divided V average by R. So minus 1.16 divided by 20 will give a current of minus 0.758 amps. Similarly, I can calculate the RMS output voltage, which is Vm by 2 root pi under root 2 pi minus alpha plus 1 by 2 sine 2 alpha. So we know alpha, which is 45 degrees. We know Vm, it is 230 into root 2, right? So if I substitute here, now Vm 230 into root 2, 2 root pi under root 2 pi minus alpha, 2 pi is 180 minus alpha 45 degrees. So here you can see it is pi by 180. So because this value will be in degrees, to convert this degrees into radians, we need to multiply with pi by 180. So that is why I have multiplied with pi by 180 plus 1 by 2 sine 2 alpha, 2 into 45 degrees. So that will give a voltage of 224.5 volts. And I can calculate the RMS output voltage current. So V naught RMS by R, that will give it as 11.225 amps. And input power factor will be given as V naught RMS divided by V supply. So if we know the V naught RMS is the expression for V naught RMS, and we know V supply, which is root 2 times Vm equal to V naught Vm equal root 2 times V supply. So from that one, this will be the expression for input power factor. And if I substitute alpha, I can get 0.95 lagging. I have mentioned here lagging means it is having some inductor effect. That is why it is approximately equal to unity power factor, but due to presence of the source inductors, will be having some inductors. We need to consider that factor into consideration. right? So this is the input power factor for the given problem. So with this, I will stop here. And in the next video, we'll see the single phase full wave AC voltage controller. Thank you.